B part 4, lecture 14. Now, definition, action, also called Hamilton's principle in field theory. Action or Hamilton's principle is the same. Action principle or Hamilton's principle. So, in the field theory, we aim to describe physical system by assigning field values at every point in the space-time. Remember, every point means Eulerian viewpoint, you see, as we emphasized on the previous videos. Again, and not just along particle trajectories, Lagrangian viewpoint. That's important to emphasize here. So, for a field phi function of x mu, attention now, of this mu over here, defined over space-time, this is a 4-dimension. You see, that's a point, that's a time. So the action is a functional of the field. S phi is integral. You see, this omega here represents the fourth space. You see, so this is Lagrangian phi. That's attention now. If phi is a scalar, you see, partial of phi with respect to x mu is components of a gradient, and I wrote over here. So this is integral over the fourth space, where phi is a scalar if attention now, if, that's what over here, if phi is a scalar, then this partial of phi with respect to x mu, you see, they are components of one form. This is the phi, you see. This belongs to cotangent space. So this is written over there, you see. Now, so the phi is a covector which belongs to the cotangent space T asterisk M. See, that's to reinforce, see, about concepts we already saw, we already derived in previous videos. So, we already did this in classical mechanics. Now my goal is to see the units. In classical mechanics, the action is defined as, you see, S is the action, okay? The integral from T1, T2, attention now, this is integral on dt, the time. So the units of the action is clear, you see, will be the units of L times the unit of dt. The units of L, remember that L here is length, okay? Is the Lagrangian, in this case. See, you can write, you see, the units of Lagrangian, okay, as L minus TV. Attention now, you see, that's important. T over here, as I said, is a function, is a kinetic energy, okay, with 1/2 of m, the mass, times v squared, you see. In the case here, v is q dot. This is already derived here. So, since kinetic energy, I'm repeating, T is 1/2 of m v squared. The units of T, okay, is m L of T. Don't confuse this T over here with this T over there. T here is kinetic energy, that's and T here is the time. So, the units of T, kinetic energy is the same, the units of the potential energy. This is energy, okay? This is energy. In general, in joules, in the international system of units. Since the unit of dt is a capital T, this is time. Don't confuse with this T over here. So the unit S is a unit of L, okay? I said that unit L is not length. Unit L here is energy. So it's energy times the unit of time. The energy is mass. You see L of T is V. So this is mv squared times the time here. So then grouping this is ml squared over T is ml squared T minus 1. So this is a unit of the action. Then I can write action is energy plus time. Energy, you see the integrand, okay? And this dt, that's the time. So it's clear. Now, attention now I will move to the field theory. You see, action in classical mechanics, you just write over here, and you remember that we derived the Euler-Lagrangian, okay? Just using this action over here. Now I'm in general, okay? In general, in the field theory, which classical mechanics is a particular case of this field theory here. So S of phi is integral. Attention now, phi, gradient of phi is scalar. If it's not, gradient of phi is a second order tensor. So this derivative here, it increases by 1 the order of the tensor. Since phi is a scalar, the gradient is 1 degree ahead. So this is one form. So there's a one form here. And this is d fourth. Right there, d fourth x. You see? That's a volume by time. d4x, where now in the field, okay, field theory, which classical mechanics is a particular case of the field theory. Now, the action is energy times time, it's the same, okay, doesn't matter if it's classical mechanics or in the field theory in general. So I can write S the same as I did over here. So this is universal, whether for a point particle or a field, doesn't matter, okay? The action S, the unit is energy times the time. So, in natural or Cartesian coordinates, d fourth of x is the x dy dz times dt. The unit is L squared, the volume. L here, attention now, don't confuse. L here is not Lagrangian. L here is length. So it's length cubed times t. Solving here for the integrand L, this is the action S divided by d4x. So you just cancel here. So this is a unit of the Lagrangian here. See, it's m L minus 1 t minus 2. Observe that L is energy divided by volume. Okay, that's because the integrand and this definition over here leads to this what I wrote over there. See, so this is action. Now we'll move to the Noether theorem. Okay, that's the next video. So you use all this concept, okay, that we are doing and motivating just to use the Noether theorem.